William suggested I start the interview looking like this and then I turn. My name is Mohammad Dmour. I'm a senior research engineer at AudioTeligence. I've been working at AudioTeligence for over 3 years. I've been working on audio signal processing for over 15 years. It all started when I did my PhD at Edinburgh University, and the topic was audio source separation. Well, we live in a noisy world, so often the speech we would like to listen to is contaminated with interference, noise, and reverberation. This can affect the quality and the intelligibility of the speech. Therefore, it's essential to apply some signal processing techniques in order to try to increase the quality of the speech signal. This will help us better understand what's being said, and it will reduce the listening effort. One of the well-known methods to extract a target source from interference and noise is called beamforming. In beamforming, we use a microphone array, so we need more than one microphone, and we filter each microphone signal and then sum them together. We do that in order to try to combine the signals arriving from a certain direction coherently, while the signals arriving from other directions are combined destructively. This will have the effect of preserving the target source while attenuating the noise and interference. In general, beamforming will require you to know the microphone geometry and the location of the sources or the target source relative to the microphone array.
Mohammed, are there different types of beamformers?
Yes. Beamformers can be classified as data-independent or adaptive. Data-independent beamformers will not depend on the content of the observed signal. One of the most well-known data-independent beamformer is the delay and sum beamformer. In the delay and sum beamformer, the microphone signals are delayed such that when we sum them, the target source coming from a certain direction will experience coherent combining, expecting that signals arriving from other directions will suffer to some extent from destructive combining. In many audio consumer applications, this will have a very small benefit. And the reason is typical consumer devices have a small number of microphones and the size of the microphone array is small. For delay and sum beamforming to do a good job, we need the wavelength of the signal to be small compared to the size of the microphone array. But the low frequencies of speech have a very large wavelength, which is in meters. In adaptive beamforming, the filters are designed based on the statistics of the observed microphone signals. One of the most well-known adaptive beamformer is called the Mvdr Beamformer, which stands for Minimum Variance Distortionless Response Beamformer. In this beamformer, we try to pass the signal arriving from the target source in a distortionless way, while attempting to minimize the power at the output of the beamformer. This will have the effect of trying to preserve the target source while attenuating the noise and interference. This can work really well in ideal lab conditions. However, in the real world, there is microphone mismatch. Sometimes there is an inaccuracy in the desired source location, and there is reverberation. This can lead to poor performance of these beamformers because what we might end up with is that the beamformer will start canceling parts of the target source. In Mvdr beamforming, just like the delay and sum beamforming and most beamforming types, we require the knowledge of the microphone array geometry, the target source direction, and we require calibrated microphones. In order to address the target cancellation problem, we can add a voice activity detector and turn off the adaptation of the beamformer when the target source is active. This can work really well. However, if there are multiple competing speakers, this can have limited effectiveness. Anything else?